Data scientists often praise NumPy for its power. SciPy looks at NumPy and thinks, adorable. SciPy is not here to perform basic calculations. It integrates, optimizes, transforms, and solves. This is a library for those who have mastered simplicity and are prepared to embrace complexity. Let us explore SciPy, where mathematics meets precision engineering. Shall we begin? Install SciPy. SciPy is no ordinary library. It is a collection of specialists. Each module is a master of its domain, from calculus to optimization, from statistics to linear algebra. Together, they provide you with a robust mathematical toolkit. Start with constants, immutable values that never change. Move to integrate, where derivatives, integrals, and differential equations are solved with machine precision. Then there is optimize, for finding the highs, the lows, and everything in between. The linear algebra module has it all: matrices, vectors, eigenvalues, and stats equips you with tools for rigorous statistical calculations. SciPy is modular by design. Each part can work alone, but together, they solve problems in concert, like a mathematical orchestra. SciPy's constants module gives you access to a catalog of commonly used values. For instance, let us retrieve the speed of light. Run. Now let us convert it into kilometers per hour. People do love their unit conversions. Run. The result is a speed so fast it feels theoretical, but rest assured, it is grounded in reality. Of course, the speed of light is famous. Everyone knows c by name. But what about those lesser-known constants? You will be pleased to hear that the constants module includes the find function for searching through the list of constants. For example, let us look for all constants related to electron. Run. Admire the results. All your electron-related numbers are here. In calculus, SciPy focuses on integrals. There used to be a derivative function, but it was deprecated and removed. This is because NumPy and other libraries have superb derivative functions. Consequentemente, our focus will be on integration. Let us start with the quad function, which computes definite integrals. Here we compute the definite integral of sine x from 0 to pi. Run. The result? 2, with an error so small it is practically negligible. SciPy can also integrate over the entire real line. Here is the Gaussian integral from negative infinity to positive infinity. Run. SciPy's numerical result aligns perfectly with the theory. In a world where search results are flooded with AI-generated content, finding genuine, thoughtful resources feels like searching for a needle in a digital haystack. That is why we built our website. Real courses, made by real people, for real learners like you. Really. Do check us out at Socratica.com. Optimization is the art of finding the best solution, or sometimes the least bad one. SciPy's Optimize module provides tools to locate minima, solve equations, and fit models. Let us start with function minimization. We first define our objective function. Then we call the minimize scalar function. There are several optimization methods available. We will use the bounded method that restricts the search to a specified interval. First, pass in the objective function. Next, provide the bounded interval. Finally, select the bounded method. Run. We use the x property and the fun property to access the x-coordinate and function value of the minimum. Next, we will use the optimize module to find an approximate root to an equation. First, define a function that represents one side of the equation. The root scalar function will try to find a point where this is 0, given a search interval. Run. If a root exists in the interval, its approximate value is stored in the root property. For our last example of the optimized module at work, we explore curve fitting. We will create a collection of x coordinates. Then we will compute the corresponding y values. For this demonstration, we will add some noise to each y coordinate. Next, define the function form you want to use to fit the data. The first parameter is required to be your input. Now call curve fit and supply the model, x values, and y values. Run. The curve fit function returns two objects. The first is a list with the estimated parameters. The second is more technical, the covariance matrix of the parameters. If we print the fitted parameters, we see that the values for A and B are excellent approximations for the function used to generate the data. While NumPy has its own robust linear algebra capabilities, SciPy adds additional features with their linear algebra and sparse packages. First, solving systems of linear equations. This can be done using NumPy, but this is a SciPy video. For example, consider these two equations. We represent them as a coefficient matrix in a constants vector. The solve function computes the values of x and y. Run. The solution is precise, as expected. Next, eigenvalues and eigenvectors. For symmetric matrices, the eigh function provides an optimized approach. Here we compute the eigenvalues and their corresponding eigenvectors. Run. The results are critical for applications like principal component analysis and everybody's favorite, quantum mechanics. Finally, let us explore sparse matrices, an area where SciPy surpasses the world of NumPy. These are large matrices with many zeros, where storing every element would be inefficient. The sparse module optimizes the storage and uses of these mostly empty rectangles. Observe this tri-diagonal matrix. Although it is 1,000 by 1,000 in size, only 2,998 elements are stored instead of 1 million. Run. You can look around, and there is not a sign of inefficiency. Nothing but efficiency as far as the eye can see. People love a good story. Statistical analysis and inference is what turns data into story time. Once upon a time, SciPy unleashed a stats module. Let us explore 3 little tasks. First, generating random data. The RVS function creates datasets from predefined distributions. For example, here we generate 2 datasets from normal distributions with different means. Run. These will serve as the basis for our analysis. Next, hypothesis testing. The t-test-ind function tests whether the 2 datasets have the same mean. Run. The result includes a p-value, which tells us whether the difference in means is statistically significant. Here, the p-value exceeds 0.05, so we cannot reject the null hypothesis at the 5% significance level. Finally, fitting distributions. The fit function estimates the parameters of a distribution from data. Run. Comparing the fitted parameters to the known values confirms their accuracy. And they all lived happily ever after. The end. Congratulations! By completing this video on SciPy, you are now, by the powers invested in me, officially a data scientist. This title comes with all the rights and privileges thereof, including but not limited to saying, "I'll have to run the numbers on that," in casual conversation, rolling your eyes at poorly labeled graphs, and a legally binding obligation to yell the word interval when you hear the word confidence